Hello and welcome to Trump. My name is Brett Thompson. I want to talk about some different ways of cutting aluminum today. So what we're going to do is we're going to look at a couple different thicknesses, kind of the mid-thick stuff, 1/4 inch, go with something a little bit thicker, 3/4 of an inch, and then go all the way down to the bottom, around 11 gauge, 10 gauge, that range, and just look at different ways that we can affect the cut quality of parts and then the performance that we're going to cut with. And so to look at a couple of different samples here, starting with the small stuff, we have a nitrogen cut part. This is 5052 aluminum, if we can see it. And that's a pretty good edge quality. Now, the more laser power we have, the better the edge quality is going to be. Also, of course, the faster it's going to be, but then also the less of a burr you're going to have on the bottom. But there are also ways that you can address that without necessarily buying more laser power. Now, what we prefer to do is to actually use an oxygen process, though you can use what we're going to use on the thicker range, which is a mixed gas. The mixed gas really doesn't give us much of a benefit when it comes to speed, but it does give us a nice edge. If you look at that, you can see it's a little bit better than we had with nitrogen, though I would say this is a process that is best left actually for the thicker stuff, because we can do this. This is an oxygen cut. It's a low pressure oxygen cut. Doesn't really require anything special on the machine, but what it gives us is really, really high speeds, and also not only good edge quality, but also very little burr on the bottom. And we're going to be cutting this with only 4 kilowatts. So obviously, if you have more power, you're going to be able to go more quickly. But you're going to see about double the speed here, and even greater than that when the material thicknesses are a little bit less. And then when we move over to the thicker materials, so here's some 6061, 3/4 of an inch, cut with nitrogen. Now this is, pretty common for 6061. It's a pretty viscous material. The carb or the magnesium and silicon, the material will give us a little bit lower speeds and a little bit more of this burr. The alternative could be that you process with nitrogen something like a 5052. Now, this will cut better, but of course, this is going to be a more expensive part. I'm not going to be bending it. I'm not going to be laser welding it. So maybe it's going to be cost prohibitive. So this is really where a mixer comes into play. So this is that same 6061 material, but with really, really good quality, right? So we have very, very little burr on the bottom, and we have really nice, smooth, homogeneous edges. And that's really going to be a result of the mixed gas operation. So having a look at my screen here, what we want to just kind of look at is what's really required here. So we're going to be seeing 3 different kind of processes today. Your general purpose, what we see over here in these large tanks, that's nitrogen. That's normally how we would cut these materials. Like we say, we have, of course, also the ability to cut with oxygen. And oxygen is really good in aluminum up to about 1/4 inch, which is what we're going to be working with today. And really the reason you wouldn't go past this is because you get a little bit unstable at that point. So that's really the upper limits. When you get beyond that threshold, though, when you get into the thicker aluminums, where typically fiber tends to struggle a little bit, that's where using a gas mixer to create really high quality parts becomes really advantageous. Now, obviously, the reason that we like the oxygen, or maybe not obvious, but as I had mentioned previous, it gives us a really big boost in performance. So I grabbed just some different values. And again, this is only 4 kilowatts. We're not even looking at what we would have with really high powers. If you go to the really thin end of the spectrum, you're 150%. If you go to the upper threshold of really what's achievable, which we'll be doing today, you get 97%. Now, if you look kind of in the middle here, you see really big gains. So 80 thousandths, 120 thousandths, 3/16, you have pretty big gains, the largest being actually at the 11 gauge. So the reason that we have such a big uptick in speed at the 11 gauge is that's when we would actually switch to our low pressure, high speed nozzle. So just that nozzle technology is going to give us a little bit more speed, but you're talking about a low pressure process, so you're not using actually a lot of nitrogen at this point, and you're getting 340% over the base feed rate with 4 kilowatts. So that's pretty impressive. Then again, when we're cutting with the different alloys of material, this is really on the thicker end where we have to consider the processes. A 5 series aluminum does cut really well with just your standard nitrogen process, but even on the 5 series aluminum, you're going to really clean that edge up and really reduce or eliminate altogether that microburr that can kind of form because of the viscosity of the aluminum materials. So it's really advantageous for doing thick aluminums and material qualities. And this is something very likely that we'll look at in the future as well, in relation to kind of addressing burr cutting steel with nitrogen. So there are other applications for a mixed gas, but really again today the focus is going to be on aluminum materials processing. And so what we're going to do is we're going to jump over to my friend and colleague, Mr. Gamache, and he's going to actually run through the different parts that I showed you on my desk today. And then we're going to have, of course, a question and answer session at the end if anything pops up in your head that you want to address. Okay, James, go ahead and take over.
Hey guys, how's it going? Today I will be demoing some different aluminum technologies on our kit here in our showroom. We're going to start with 1/4 inch, like Brett was talking about, and show you 2 different styles of cutting in that. So the first thing we're going to run is our standard nitrogen cut. So let me just use our drop and cut camera here. This is a cool little feature on these machines. It allows you to take an active nest and rework it with this post-production tool and actually use the camera that comes with the machine to pick and place the part. You can fine tune it. As you can see, I'm kind of just moving it with my arrows here, but you can rotate it fully in 360 degrees, 1 degree increments. So really handy, saves a lot of time on the shop floor, not having to go back to it or anything like that.
So James, if you're working with the drop and cut camera, it's pretty cool too, because we could also say have 3, 4 different parts that we put into like a mini nest, right? So we could have one piece for this orientation, squeeze another one in there. I've got this drop laying around. Rather than throwing it in the recycling bin, I might as well make parts out of it. That's kind of the purpose, right?
Right, exactly. And you know, it lets you utilize a lot of the material that's in your shop. You know, all the weird drops that you have and all that stuff. You know, we know that sometimes the press brake guys bend stuff backwards. They need another part. You know, they come up.
Nonsense. As a former press brake guy, I've never been a part backwards, James. That is slander. But nevertheless, it's definitely a cool thing to have.
So we're going to go inside the machine now, do a little nozzle change, and then cut with nitrogen. This is going to be at 4 kilowatts, like we talked about earlier. This is at 102 inches a minute.
We're actually looking at, there we go, that's better. All right, so we're doing a nozzle change operation now. And you know what's interesting about the nozzle, maybe we point something out here, our nozzles are being screwed in as opposed to being pressed in, which is, you know, kind of a common way of setting a nozzle on a laser machine. The reason we use a screw-in nozzle as opposed to a pressed-in nozzle is this guarantees concentricity. So whereas usually when you do a nozzle change, technically you're supposed to do an alignment of the nozzle to make sure the beam's in the center. We never really have to do that because we're always ensuring that the nozzle is going back into the exact location it's supposed to.
Correct. All right, just finishing up there, a little loop cycle, and it's off to the races. So we're going to see it do a little etch here first.
And this is
Trump
nitrogen?
logo. Correct.
Okay, and how much power?
So 102 inches a minute, 4,000 watts.
4,000 watts. So we've scaled this machine down to show the boost in performance, right? So if you don't have a whole lot of laser power, obviously cutting with oxygen is going to give us more speed, but that's also true with higher laser powers. So if you have you know, a laser pumping out a little bit more juice, it's something that would be applicable. We just kind of want to show how much scalability there is for this.
Exactly. All right, just about finished there. Let me pull this part out and show it to you guys. Micro joint. All right. Get it up for you guys here. So hopefully everybody can see that in nice fine detail. So again, nitrogen cut, 102 inches per minute. We can see the underside quality there. Kind of see the burr. Pretty standard for a 4 kilowatt.
All right. And what alloy of aluminum is that, James?
So this is a 5052 H32 alloy.
Okay.
All right. On to the high-speed oxygen.
Are we using a special nozzle for this application, or is it the standard nozzle?
So for the high-speed oxygen process, we actually use the EAU100 nozzle, so a dual orifice nozzle. It's actually the nozzle we're using for our high-speed processes for steel.
We use that because of the low pressure then?
Yes, exactly.
Okay. So, you know, kind of like with compressed air, which is the last topic we did a webinar on, you can only generate so much pressure and volume, right? So people might get angry with us if you're, you know, sucking your relatively small tank of oxygen dry really quickly. So this allows us to have, you know, of course, high speeds without going through a couple tanks of oxygen a day. But
right. Actually, an interesting thing is the nitrogen uses, I think, twice as much gas. It uses around 16 bar of gas as opposed to around 7 bar with the oxygen.
Oh, wow.
So you're cutting twice as fast, kind of similarly to the high-speed or high-speed eco. You're cutting twice as fast with half the gas pressure.
Mm-hmm.
All right. So again, I'm going to start with a little marking here. And you'll notice not just the cut speeds here, but how much faster it pierces. So this is 202 inches per minute. So we're 100 inches a minute faster here than we were cutting with nitrogen.
Might want to switch here. Your sound keeps breaking up.
All right.
Oh, you're nice and clear. Clear as the sky is blue. So yeah. One thing we might consider about this, though, so I think from some of our experience, this is definitely a really fast process. That's a complete upside. If you're painting it, paintability is not an issue. I do believe that there would be maybe some limitation to welding this, though, because of the oxide. Is that correct?
Yes.
Mm-hmm. So if we were to weld this part, we would just have to treat the edge, which could be a little bit deceiving because we're used on a steel cut to say, oh, you've got that little oxide layer stuck to the side that flakes off. So it's very visibly easy here. You just have to treat the edge to get rid of the small oxide layer on the material before you weld it. No big deal.
So just pull up both of these parts for you guys so you can take a look at both of them at the same time. So we have the nitrogen part right here, and we have the oxygen part right here. So you can see the burr is a lot lower on the oxygen part. There's the underside of it there, as opposed to the underside of our nitrogen cut part. And you'll also notice on the oxygen part, the really nice smooth side edge. There's no striations or anything like that. It's very homogeneous. Mm-hmm. Really, really nice. Almost like it's looks like it's been cut on a water jet or something like that.
Yeah. And we would stress too that with the nitrogen part, the lower speeds that we'd see on this machine normally, the little bit more burr than you would typically expect is because we scaled the laser power down to show really the boost across that lower material range. So this is an 8 kilowatt laser. This is also offered in a 10. In either of those scenarios, of course, we'd be cutting a lot more quickly with nitrogen, and you'd have realistically no visible burr in that thickness range. But to show you really what's capable without having anything special, there's not a special system that's required. There's not even really a special technique that we're using here. It's just a low pressure oxygen process, and it doesn't require huge amounts of power to gain high levels of speed.
Right. All right, moving on to something a little thicker. So I do have some 3/4 inch in here. It is a 6061 T6 alloy, and we will be using the mixer to cut this part. We're going about 7 inches a minute here, using a 97% to 3% oxygen mix.
In that
Another
mix,
nozzle change here.
The mix is something that we've just empirically come up with, right? So it's not a set value. So if somebody said, I find with this material thickness or with this particular alloy, maybe a different ratio of oxygen to nitrogen, or I mean, realistically, any sort of mix of gases, I would assume like an inert with a non-inert gas. It's really up to the end user, I think, right? This is just what we found really works for this material.
Right, right. It's a nice quick pierce there. Nice tiny hole.
So what's the laser doing during the pierce? Are we using any special technologies or anything at this point?
So we are using the pierce line sensor. So that's you know, looking at the pierce, and it's basically dynamic. It knows when it's through. But we are using a piercing with a widening, so it does cut like a little hole, I guess you'd call it, and that just really ensures that your pierce is nice and has a good size to it, so that the gas can really start flowing well. That really helps initialize the cut and keep it going good.
Okay. What's our beam diameter for this?
So our beam diameter, we are using Brightline for this. So this is an 840 micron beam. So that's going to give us a really nice straight side edge. It's also going to make the part a lot easier to come out. I don't know if any of you guys listening have cut 3/4 aluminum, but when you cut it with nitrogen, it's a pretty tight fit, and sometimes it's kind of hard to get the parts out. With the reduction in burr here and with the significantly smoother side edge, it tends to drop out of the sheet a lot easier, which I'll show you guys in just a second once this part stops cutting.
Yeah, and I would say too with the Brightline fiber, so to any of you out there who don't know what it is, it's not just like light collimation where you're using optics to create a larger beam, shrinking up the waist of the laser, or changing the position of the beam's relative Rayleigh length, or using like a beam shaper in line. It's actually using two different cores. So when James is piercing through the material, we want to get through that stuff nice and quick. And so he's going to use a small interior core, the same core diameter as anybody that doesn't have Trump on the side of the machine is going to use, 100 micron. And as soon as our little pierce line sensor detects that we are at the end of the pierce, it says, okay, well, you need to switch over to a large core diameter now. So it actually goes to an outer core that is substantially larger. And this is really where we get the better quality, but that quality is really indicative of stability. So James is doing a 6,000 material here because, quite frankly, it's cheaper. That's what we're allowed to buy. And so whether we're cutting thick aluminum, thick stainless, thick steel, if you get variations in alloy, variations in surface quality, just variations in the composition of the material, it makes it much more forgiving because the beam is so much bigger than you can get with a system that doesn't have Brightline.
All right, guys, so I have this nice part here that we just cut. And there is our side edge. So this is the bottom side right here. Right here, that is the bottom side. So you'll see a really, really low burr. Very, very nice side edge with really minimal striations. It's very, very smooth compared to a nitrogen cut. Nice and straight too, you can see it there, very perpendicular side edge. Actually, let me put this down and grab a nitrogen part that I cut a little bit earlier today, just so you guys can see what I'm talking about. So exact same part geometry, it's actually the same program and everything, but you'll see the higher burr here, about 10 thousandths higher of a burr. And you'll notice that the side edge is significantly more striated, so there's deeper grooves in it as opposed to our mixed gas sample. And this technique works very similarly, really up to the top end of the range on these machines. So like 1 inch would cut very similarly. So let me show you side by side here. So here's our mixed gas on this side and our nitrogen on this side. Get a little side by side comparison, so you guys can really see that difference there. Really see the difference in the burr. Show that nice little hole for you guys. Actually, a nice little hole in both of the parts. It's about a 5/16 hole. All right. So let's switch gears again here, and let me switch my palettes for you guys and move on to a little bit different of a thickness of material. So the next thing we're going to cut is 120 thousandths of an inch aluminum, and we'll be doing this with both nitrogen and oxygen to show you guys a really really awesome comparison, really show the speed difference here.
So this was the material thickness on my chart that had the largest performance difference. That was 340% faster with oxygen than nitrogen.
Oh, I believe it. It is wicked fast.
It is wicked fast, absolutely.
All right. So let's go with the nitrogen cut first. So going to do another nozzle change. So this is going to cut with nitrogen at 303 inches per minute.
Yeah, how much power are we using?
We are now at 8 kilowatts.
Okay, so we'll use 8 for both then.
Correct.
Okay.
Doing a little control line calibration. And it's off. All right. Take this part out for you guys so I can show you the side edge. In these thinner materials, typically the side edges are very, very good, whether you're going with nitrogen or oxygen or even air. Typically very, very similar. Hold this up here for you guys to see. Get it nice and close. It's kind of thin. So this is the bottom side that you guys are seeing right there. So you'll notice no real burr or anything like that. Nice looking side edge. Really overall a really nice looking part. But let's switch to oxygen and take a look at that. All right. All right. So I believe that this will do another nozzle change on me. So the main difference here won't be the quality of the cut. They're both very, very similar in that regard. What we will notice here, like Brett was talking about earlier, is the increase in speed. So this goes from around 300 inches a minute to 1,770 inches per minute using oxygen. So a huge leap there.
That's more numbers than the nitrogen one.
Yeah. And you'll notice this in this part, mainly in the long straightaways, but also in the smaller contours. I do have micro joints turned on this part for those small outside circles.
Whew, boy, that is.
You really notice it. You see it on that outside. See how fast that was?
That was barely, but yeah, I saw it. So the
What
reason
happened?
we didn't run this on our 12 kilowatt is you wouldn't be able to see it. It would just be over.
Yeah, right. We have to do like a slow-mo playback. Knock out all my micro joints here for you guys. And there's our part. So you will notice on the side edge of this part, just like the 1/4 inch, it's got that kind of sandpapery, smooth edge to it. A little bit different looking than the nitrogen, not really striated at all. But you'll notice again, no burr on the underside of that. Just a lot faster.
All right, very good. Thank you very much for that, James. I think what we'll do now is we'll see if there are any questions in the question area, and surprisingly, there really aren't. Wow, we're used to having a whole bunch of questions here, but does anybody have any questions or just want to comment on how great of a job James did or how good he looks with that beard? You know. I guess not. Well, and I tell you what, y'all have our contact information, and if a question were to come up, you said, okay, I have some interest. Oh, here's a question. What about stainless? Is it better or no gain? A gas mixer and stainless? You could theoretically have a similar reaction to what you might see when you're cutting with steel. Generally, we can push the threshold for stainless to a greater limit with nitrogen. There's no carbon in the material, and do so without really generating an inhomogeneous burr or edge or a burr. And so really, you might gain some sort of benefit, but the thing to keep in mind with stainless is if you introduce a non-inert gas, you're going to contaminate it. So if it's a structural component or something, yeah, you might consider using a mixed gas, but at that point, actually, it's not a bad idea to just consider compressed air. The machine that James is running today, he can do up to 1 inch with just a normal screw type air compressor. So there's nothing really necessary there, equipment wise as well. So I would think from a stainless perspective, maybe mildly there could be a benefit. I think there is more of a potential benefit for steel because you could address, I think, the burr limit at the capacity for the material a little bit more. Let's see what else.
Definitely.
We got a whole bunch of, I'm glad you're here to fact check me. So we've got some more questions popping up here. So is the gas mixture shop air? Nope, the gas mixture is actually 97% nitrogen with 3% oxygen. And that's a value that could be adjusted. So we find that if you're using this on steel as opposed to aluminum, the oxygen content is maybe a little bit higher with steel. It seems to have a little bit more of a benefit for burr, addressing the burr. That value is not set in stone. That's just kind of something that we've played with. And, you know, I've seen that there are even a number of, you know, folks in the air industry on the meeting today, and they might have more information as well about what are the different ways that you can mix different types of gases or at different quantities to achieve, you know, maybe better quality, maybe better performance, sacrifice one for the other. But as it is right now, what we had focused on is nitrogen and oxygen, 97 to 3%. As far as a photo of the side edge, we can certainly do that. So we can send out a little bit of information afterwards to pretty much everybody on the list. If you want, I'll actually ask Mike if he has a way to do that. If he doesn't, please do feel free to contact me or Mike, and he can forward your request to me, and we can make sure that we send pictures, not only what James has worked on today, but if you had a particular material in mind, maybe a certain power, a certain machine or something, we could also address it and say, here's what the results would look like on a material that you requested or even a part. So I have one, we have an older L49 with the no eco nozzles. Well, so Nick, it requires really the high speed, not the eco nozzle. You wouldn't use the high speed eco in this scenario. The high speed nozzles have been around longer than the eco. So you might look at whether you have an EAU 100. So it'd be the dual orifice nozzle. And James, I might need your input here. Is there any restriction from a control perspective using that nozzle on a machine that has like a certain generation control or anything?
Yeah, some of the early L49s would be incompatible with that nozzle, but most of them are able to use that nozzle. Mm-hmm. So we'd have to check it.
Okay.
But so they have the EAU style nozzles as well, like the 60, 40, 25, and 30. And they're, you know, it's possible to make tech tables with those as well. They won't be as fast, but it is possible.
And so, but in theoretically, we could have a high pressure oxygen system too, and there are even generators for such a thing. Yep. So if you said, I don't have a machine with the appropriate nozzle technology, theoretically, you could either buy bulk oxygen at a higher pressure, or there are actually even generators for oxygen. Yep. So that would answer, you know, some of the other questions I have here, like with an L29 or using standard nozzles. Hashim Kamal said that you look great with the beard, James. So that's really what we're shooting for here. So I think we can go home now. I got to grow mine out. I actually shaved a little bit today, as you know.
Yeah.
So I had a question about the wattage. So we were using an 8 kilowatt machine. running at 4 kilowatts. And really, we wanted to show that you don't need a huge amount of power to cut with very high speed in aluminum. Maybe it shows, I think, using all 8 kilowatts really well when we did the 11 gauge material, because you see really how fast you can go, but you can still get really impressive performance as well as quality gains using an oxygen cut on 1/4 inch, which at a normal 4 kilowatt cut's a little bit slower with that nitrogen process.
Yep.
So we do have a question using oxygen to cut stainless steel. Well, I've seen oxygen cutting in stainless steel, and it's certainly something that can be done. But again, it comes down to that question of contamination of the materials. You would have a similar sort of scenario to like a plasma or an oxyacetylene process, where you would have great capacity. You would have good speed, and in a matter of fact, there are applications where we will use oxygen to pierce through very thick stainless steel, because you can achieve quicker piercing times than with using just a straight fusion process with nitrogen. So it can be done. It's just not something that normally is done because of the contamination of the material, but you could certainly do it. So the purity level of the oxygen came up. Now, we definitely aren't using 100% pure oxygen. So I want to say, what are we, 99.9, or is it 2? Is it even that high?
I believe it's 995.
995.
European standard equivalent is like 3.5. I believe what we're using. So it's pretty standard oxygen that we're getting.
And so with that too, so that is what is requested in our install guides, and I don't think that's actually what we buy. I think we use lower purity oxygen.
Probably.
Yeah, exactly. I mean, that's what our customers deal with, right? So we're not going to buy medical grade oxygen, and I don't think most of our customers are buying the same. So there's, we put in the installation manuals the same sort of caveat. Hey, if you cut with a lower purity nitrogen and stainless, you're going to contaminate it. But most people might say, well, I don't care. It's not medical. It's not food. So I'm going to, be chopping up some 400 series stainless that already has carbon in it. So, who cares? So the same thing can apply here with oxygen. You can use a lower purity. So you might have better results actually from a performance perspective if you have, theoretically even hotter beam, but we're definitely not using pure nitrogen. It's a little bit lower, pure oxygen. It's a little bit lower than even what's specified. So let's see, what do we have here? So does the oxygen compare to the gas mixer finish on aluminum above 1/2 inch? And that's a good question, because you can actually use it above. Realistically, we're finding around 1/4 inch, 3/8, maybe not even 3/8, James, probably more like 5/16, right? Where stability kind of goes away.
Yeah, once you start to get really thick, the oxygen, can start to become unstable. Starts to kind of explode. But yeah, once you get a little bit thicker than that, the gas mixer would definitely be, if you wanted that higher quality edge finish, the gas mixer would definitely be where you'd want to look. And I would say that you'd probably want to start mixing at around 1/2 an inch. If you have a lower laser power, then it's definitely beneficial into the 3/8. But if you have like a 6K or greater, 1/2 inch is probably where you'd want to start.
Okay, yeah, that makes sense. There's just definitely a question of whether we're hitting a stability issue at a certain point or not. And we've really run into our 30-minute barrier, everybody. So unfortunately, we're going to have to shut it down. And there are a couple questions left. So what I would say is, you've got more questions, certainly either submit them to myself if you have my contact info was up there briefly. More likely what you would have is Mike's contact info. He's the gentleman who sent out all the invites. So if you have questions about what you've seen or applicability for this machine, do you need new techniques, new technologies, things like this, just let Mike know. He'll send those questions on to myself or to James or to Soleil, and we'll make sure that we get them answered for you. So from all of us here at Trump, both from my home and from the factory, have a great day, and thanks for joining us.
See you guys. Thanks for coming.